Let's look at integrating inverse hyperbolic functions. First, we have the integral of 1 over the square root of 1 plus u squared du equals the inverse hyperbolic sine of u plus c. Similarly, the integral of 1 over the square root of u squared minus 1 du is equal to the inverse hyperbolic cosine of u plus c. Next, recall that the derivatives of the inverse hyperbolic tangent function and the inverse hyperbolic cotangent function are both equal to 1 over 1 minus x squared. So, when we integrate this, we must take into consideration the domains of the functions. This means that the integral of 1 over 1 minus u squared du is equal to the inverse hyperbolic tangent of u plus c if the absolute value of u is less than 1, and the integral is equal to the inverse cotangent of u plus c if the absolute value of u is greater than 1. Now, let's move on to the inverse hyperbolic secant function. The integral of 1 over u times the square root of 1 minus u squared du is equal to the negative inverse hyperbolic secant of the absolute value of u plus c. Finally, we have the integral of 1 over u times the square root of 1 plus u squared du is equal to the negative inverse hyperbolic cosecant of the absolute value of u plus c. Let's try to solve a problem that involves an inverse hyperbolic function. In this case, we don't immediately have an integrand that we know the integral of, so let's try to rewrite it. First, we want to get the expression so that the constant under the radical in the denominator is equal to 1. We can accomplish this by removing the square root of 9. So we get the integral of 1 over the square root of 9 times e to the x over the square root of 1 plus e to the 2x over 9 dx. Let's simplify and slightly rewrite the denominator. We can rewrite this as 1/3 times the integral of e to the x over the square root of 1 plus the quantity e to the x over 3 squared dx. Notice that under the radical we have 1 plus a squared term. So, to get the integrand in the correct form, let's let u equal e to the x over 3. Differentiating, we get du is equal to e to the x over 3 dx. Substituting, we get the integral of 1 over the square root of 1 plus u squared du. Notice that our integral is now in the form of a known integral. We can integrate to get the inverse hyperbolic sine of u plus c. Finally, we substitute our expression for u back into the expression. Therefore, the given integral is equal to the inverse hyperbolic sine of the quantity e to the x over 3 plus c. Here we are asked to integrate 3 over 2 minus 18x squared dx for x greater than 1/3. This is not in any form we know how to integrate, but let's see if we can manipulate it to turn it into something that looks familiar. First, notice that there is a common factor of 2 in the denominator, so let's factor that out. That gives us the integral of 1/2 times 3 over 1 minus 9x squared dx. Now we can see that the second term in the denominator is the product of perfect squares. So rewriting the integral, we get 3/2 times the integral of 1 over 1 minus the quantity 3x squared dx. Now the integrand is in a familiar form. We just have to use u substitution. So we'll set u equal to 3x, and we get du is equal to 3 dx. Substituting, we get 1/2 times the integral of 1 over 1 minus u squared du. Recall that this integral is equal to the inverse hyperbolic tangent of u if the absolute value of u is less than 1, and equal to the inverse hyperbolic cotangent of u if the absolute value of u is greater than 1. We are given that x is greater than 1/3. This means that u must be greater than 3 times 1/3. Simplifying, we find that u is greater than 1. So, integrating 1 over 1 minus u squared, we get the inverse hyperbolic cotangent of u over 2 plus c. Substitute our expression for u, we find that the integral is equal to the inverse hyperbolic cotangent of 3x over 2 plus c.